Okay, good morning. In the last class, we have discussed about process synchronization, introduction, and then what is producer-consumer problem, and what is the need of synchronization between the processes, and then race condition. Right now, in the today's class, we are going to discuss about some of the solutions for the critical section problem. Okay, so what are the requirements for the section problem? The first one is a requirement. What is requirement? So we had a discussion yesterday. There are three requirements for the critical section solution. The first one is a mutual exclusion, second one is a progress, and the third one is a bounded weighting. What is mutual exclusion? Only one process at a time allowed to enter into the critical section. What is a critical section? Critical section is a region, so where we can keep the shared data or shared code. Okay, two process or that means more than one process is not allowed to enter into the critical section. For example, P1 process is there in the critical section. All the remaining process has to wait for the P1 to leave the critical section. Okay, that means only one process at a time is allowed to enter into the critical section. So after using the critical section shared data or code, the process can come out of the critical section. Then only the next process is allowed to enter into the critical section. So only one process allowed to enter into the critical section at a time. That is called as mutual exclusion. And the next one is the progress. What is progress? No process are there in the critical section. Few process. That means some set of process are wish to enter into the critical section. In those subset of process, you need to select one process to enter into the critical section. You got my point? There are no process in the critical section right now, but few process are entered into the critical section. In those few process or subset of process, you need to select one process to enter into the critical section. That selection process should not be postponed indefinitely. That is called as progress. Second one. And what about the third one? Bounded weighting. So whenever a process requests for the critical section, so the process entered the critical section after using the shared data or shared code, it leave the critical section. It may leave the critical section. So after coming out of critical section, the same process should not enter into the critical section again. That means you should not give a chance to enter into the critical section for a same process every time. That means once a process utilize the critical section and it come out when it come out of the critical section, immediately the process should not enter into the critical section. The process has to wait for some time and then it is allowed to enter into the critical section. Why? Because if the same process is using the critical section again and again, all the remaining process wish to enter into the critical section has to wait for longer time. Okay, in order to avoid such a problem, if a process enter into the critical section, let the process use the shared data, and then when it come out of the critical section, the same process should not request for the critical section. That means the same process should not enter into the critical section again. The process has to wait for some time. It has to give a room to the other process to enter into the critical section. Okay, so that is called as bounded waiting. Okay, mutual exclusion means only one process at time in the critical section. Progress means there are no process currently in the critical section. Subset of process are wish to enter into the critical section. In those subset, you need to select one process to critical section. Okay, that selection process should not be postponed indefinitely. And the next one is a bounded waiting. So one process entered into the critical section. After coming out of the critical section, the same process is not allowed to enter into the critical section immediately. Okay, it has to give a chance to the other process which are wish to enter into the critical section. That means all the other waiting process which are waiting for the critical section for longer time need to get the critical section. Okay, the same process should not get the critical section access every time. So that is called as bounded waiting. So the next one is a Peterson solution. What is Peterson solution? Peterson solution, we have two things. Let me explain you with the help of paint. Sorry, excuse me. So now we are going to discuss about a Peterson solution. So in the Peterson solution, we have two things. The first one is a flag. And next most important one you need to understand is in the Peterson solution, we are talking about only two processes, not more than two. Two processes. What are those? Maybe process I, Pi, and the next one is process Pj. Only two process. We need to talk about only two process, Pi and then Pj. Okay. And then here we have two things. One is a flag variable. For example, flag of I equal to true. What is flag of I equal to true? That means the process I is willing to enter into the critical section. Flag means it indicates that what is this line? Process I. That means Pi is wished to enter into the critical section. Wish to enter into critical section. Right? Then the next variable is called as turn. Turn equal to j. For example, what is turn equal to j? Turn equal to j means even though I is willing to enter into the critical section, but the turn is for j. So while you are playing carom board, so you hit the coin first, and then it will be the turn to the other person to hit the coins with a striker, right? So the turn will change every time. So in the caroms, one turn will for you, and the next turn is for your partner, and then next turn is for you, and then next turn is for your partner. Like that, the turn will rotate in between you and your partner, right? Here also, here we have only two process, Pi and Pj. Okay, the process which is willing to enter into the critical section need to set the flag to true. Okay, and then turn means whose turn? Whose turn is this? To enter into the critical section. That means you need to check two conditions while enter into the critical section. That means the process has to check. The operating system has to check these two conditions. That means whenever the process is willing to enter into the critical section, for example, this is a critical section. So whenever the process is willing to enter into the critical section, you need to check the two conditions. What are those conditions? The flag is set to the true. The flag of that particular process need to be set to true, and then turn equal to set to that particular process. For example, if a process I is willing to enter into the critical section, so what it has to check? It has to check flag of I equal to true, and then it is, of course, it is willing to enter the critical section, but the turn is also need to be set to I. That means it is a turn of I to enter into the critical section, and then process I is also willing to enter the critical section. Sometimes what happened, the turn is I for I, but the process I is not willing to enter the critical section at that particular moment, right? So because of that reason, we need to check both the conditions. What are those? If a process I is willing to enter into the critical section, then flag of I equal to true. That means it is willing to enter into the critical section or wish to enter into the critical section. And the next one, that is not enough. Wish is not enough. Ton has to be also set to the process I. So in order to enter into the critical section, process I has to check the two conditions. One is a flag of I equal to true and the ton equal to I. For example, if process J is willing to enter into the critical section, process J is willing to enter into the critical section, then operating system has to check two things. Flag of J need to be true. That means it has to be entered into the critical section with a wish. So flag of J equal to true. That means flag of J need to be true. And then turn equal to J. If these things are set, then operating system will allow the process J to enter into the critical section. That means before enter into the critical section, so each and every process has to satisfy these two things. That means the operating system will check these two things. Then only the process is allowed to enter into the critical section, whether it may be process I or process J. Only one process at a time. Only one process at a time can enter into the critical section. Okay. How many process? I told you two process. What are those? PI and PJ. Okay. What they need to do? If they want to enter into the critical section, they need to set the flag to true. Of course, both are willing to enter into the critical section. So they might both set the flag of J also will set to true. That means both the process is wish to enter into the critical section. But turn equal to I, for example, if a turn equal to I, which process is allowed to enter into the critical section? PI is allowed to enter into the critical section. Why? Because turn is I. Turn is I means it is the turn of process I to enter into the critical section, and it is also willing to enter into the critical section. So both the conditions are satisfied. Two conditions satisfied with respect to PI. Okay. Why? Because flag of I is also true. That means process I is wish to enter into the critical section. Okay. And then turn is also set to I. That means the process I can enter into the critical section. Why? Because both the conditions are satisfied. Here process J is also wish to enter into the critical section. That is the reason why it set the flag of J to true. But turn is set to I. So process J is not allowed to enter into the critical section. Why? Because turn is, now the turn is for I. Okay. Because of that reason, process I will enter into the critical section. This is the critical section. Okay. So PI is allowed to enter into the critical section first, and then after using the critical section, it will be come out of the critical section and it will set to flag of I equal to false. Why? Because the same process should not again try to enter into the critical section. Bounded waiting. I already told you, whenever the process uses the critical section, so immediately the same process is not allowed to enter into the critical section. So there are three conditions, right? What are those? First one is the mutual exclusion. And the second one is the progress. And the third one is bounded waiting. Okay. So what is first one? Mutual exclusion. Mutual exclusion means only one process at a time is allowed to enter into the critical section. Here either PI or PJ. Only one process is allowed to enter into the critical section. Why? Because either the turn is I or the turn is J. Not both. Right? Either turn is set to I or the turn is set to J. That means only PI or PJ, only one at a time only one process at a time is enter into the critical section. Okay, so mutual exclusion satisfied. What is next one? Progress. Whenever there are some process pi and pj, here in our example, wait wish to enter into the critical section, right? Flag I equal to true and flag j equal to true. These three processor wish to enter into the critical section. What we need to do? We need to select one process. Okay, we need to select one process without delaying much time, without postpone indefinitely. So here immediately whenever there is a wish, automatically we will check the value whether the turn is for I or the turn is for j. So immediately based upon this condition, we allow from one process from the set, that means either pi or pj allowed into the critical section based upon this condition. So progress okay. And then what is bounded waiting? Bounded waiting means the same process not use a critical section again and again. So for example, here in this example, pi is entered into the critical section. Why? Because flag of I equal to true and turn is also I. So immediately what happened? So pi entered into the critical section. Okay, why? Because both the conditions are satisfied. And then whenever it is leaving from the critical section, immediately the flag I is set to false. So whenever it is set to false, immediately that means it will be set to false now. So immediately I should not enter into the critical section. So whose turn is next? So immediately whenever the process I enter in the critical section, automatically the turn will be changed to j. Okay, so next time j condition satisfied, so j is allowed to enter the critical section. After that again I, likewise one time process I and the next time process j, like that they can allow to enter into the critical section one at a time. So bounded waiting is also satisfied. That means process I uses the critical section, immediately process I is not allowed to enter into the critical section. One time process I and then the next turn is for j, so process j, and the next turn is for I, process I, like that at a time only one process using the critical section and next one after the other. So these three conditions are satisfied. So Peter's solution is the solution, best solution for the critical section problem. The solution has to satisfy the requirements. The solution has to satisfy the requirements, right? So this is the thing. What I told you earlier, the same thing. So please follow the cursor. Flag of I equal to true, but turn equal to j. Remember this one here. Observe here. Two process pi and pj. Flag of I equal to true, and then what it will do? Turn equal to j. Next condition checking. Flag of j and turn equal to j. Flag of j. For example, flag of j equal to false. Why? Because for example, flag of j equal to false here. Please concentrate. Flag, follow the cursor. Flag of I equal to true and turn equal to j. For example, if flag of j equal to true, then turn equal to j, that means process j is allowed to enter into the critical section. Okay. If flag of j equal to not flag of j equal to not true, that means flag of j equal to false, but turn equal to j, that means we are giving a chance to process j, but now process j is not willing to enter the critical section. That means now we need to give a turn to I. Is it clear or not? Here the turn is for j and the flag of I equal to true. That means flag process I is willing to enter into the critical section. Flag of I equal to true means process I is willing to enter into the critical section. But whose turn it is? It is a turn of j. Okay. So whenever process I is willing to enter into the critical section, so what need to be the values? Flag of I need to be true and turn equal to I. Then only process I is allowed to enter into the critical section. So here turn is for J, but J is not willing to enter into the critical section. So flag of J equal to false. Then automatically we need to give a chance to process I. So turn equal to J and I automatically. So when the turn equal to I, automatically process I will enter into the critical section and use the critical section. And then when come out of the critical section, it need to set the value to false. Likewise, every time whenever the process enter into the critical section, the two conditions need to be verified. The turn as well as flag. Not only the turn, the process is also willing to enter into the critical section. So it need to keep the flag to true, and the turn need to be equal to that process ID. That means process I turn is turn equal to I. If it is process I turn equal to I. If it is also wish to enter into the critical section, it need to set the flag value, flag of I equal to true. If these two are okay, then only the process is allowed to enter into the critical section. And next, when it is come out of the critical section, it need to be set it to false. Why? Because when I is using the critical section, when come out of the critical section, I immediately should not enter into the critical section again. So immediately flag of I will become false. That means we have to give a chance to process J next, and then process I, like that. And next, solution to the critical section problem using locks. So first, you need to acquire the lock, and then you need to enter into the critical section and then release the lock. Okay, that means the critical section will be for only one process, right? Initially, the first process will enter into the critical section. At that time, the process need to request for the lock. If it acquires the lock, the process is allowed to enter into the critical section. Okay, at that time the lock can be opened by only one process. Okay, after that, when a process come out of that particular lock critical section, it will be free for other process. That means previous process need to release the lock, so that that lock will be acquired by the some other process. For example, here some process are there, P1, P2, P3, P4, like that. So P1 is willing to enter into the critical section, so P1 need to acquire the lock. Okay, you need to understand here, the lock will be acquired by only one process at a time. For example, P1 has a lock now. Okay, so it is allowed to enter into the critical section. So at the same time, when the P1 is in the critical section, maybe P2 is also willing to enter into the critical section. So it is not possible for process 2 to enter in the critical section. Why? Because P1 has the lock right now. Okay, so whenever P1 releases the lock, that lock can be acquired by the P2. At that time, P2 is also allowed to enter into the critical section. Likewise, at a time only one process can acquire the lock and enter into the critical section. Okay, all the remaining process are waiting for the release of the lock. Whenever the process releases the lock, and the next process can be acquire the lock, and it can enter into the critical section. Okay, the process wish to enter into the critical section need to acquire the lock. So once it acquires the lock, it can allow to enter into the critical section, and then after using the critical section, the process need to release the lock. Okay, this is the reminder section. Means what it is, reminder section. For example, if a process, for example, there is a process. For example, there is a process PI. So this is the code of a process, for example. So while executing, there is a need of enter into the critical section. Critical section code. Critical section code is nothing but a shared code. You may have a doubt. What is shared code, ma'am? What is this critical section? So I already told you when we have discussed about shared pages. For example, there are two process P1 and P2. So P1 has some code, that is ED1 and ED2, and then data 1, not data 1, it is data. Like that, P2 has ED3, ED4, and then data. That means both the processes are using the same page, same data. Here also data is there, here also data is. What we need to do whenever we want to execute P1 and P2, these two things will need to be loaded to main memory, right? So in order to execute these two processes, we need to load the process into the main memory. This is the main memory, right? So what we will do? So we need to keep P1 pages and P2 pages. So these are the main memory frames. So what we will do? So ED1, ED2 are separate pages. So we can keep ED1 here and ED2 here. And then what about ED3, ED4? So these are also separate pages, ED3 and ED4. Like that, the page, these are the pages. So these pages will be kept into the main memory frames. That means process is divided into pages. The process is divided into pages. So these pages are kept in the free frames for execution. So these ED1, ED2, ED3, ED4 are separate pages. So we keep them in a separate frame. Whereas P1 and P2 both are using the same data. No need to keep the same information in the main memory twice. For that purpose, what we will do? We'll keep only data in one frame. No need to keep this data again into the main memory. Why? Because these two are same, duplicate. So whenever there is a copy, then those pages are treated as a shared pages. So whenever there are shared pages, we need to keep it into the main memory only one copy. Okay. So whenever P1 is using that particular shared data, okay. So after executing the critical section, so whenever there is a critical section need, so then the process is enter into the critical section, and after executing the critical section, it has to come back to the process for executing the remaining code. So this is called as remaining section. That means after executing the critical section code, the process has to come back to the normal flow of execution in order to complete the next part of a program. Okay, that is called as reminder section. Okay, so now we are in the solution to critical section problem using logs. Whenever the process is wish to enter into the critical section, it need to acquire the log and then enter into the critical section. After using the critical section, it can release the log. Okay. So in the ATM centers, so only one person is allowed to enter into the centers actually. So but in our place, everyone will go to the ATM and will form like a queue inside the ATM center. But actually, so only one person is allowed to enter into the ATM. Okay. So in order to solve that queue problem and all, what we can do? So we can give you a solution for that particular problem. So whenever we enter into the ATM, whenever we want to enter into the ATM that means room. So what we need to do? So we need to scratch the card. Then only the door will open. So once the door is once the person is enter into the room, automatically the door will be closed automatically. Again, while the person leaving from that particular ATM machine, they can scratch the card and they can come out. Okay, then the lock will be released. Like that, only one person can allow to enter into the ATM machine, no other person is allowed to enter into the ATM machine when while one person is using it, right? Likewise, here also, whenever the process enter into the critical section, it has to acquire the lock. Okay, after using the critical section, it can release the lock so that the next process can acquire that particular lock. Like that means one person is coming out of the ATM room, automatically the second person can go in. Why? Because if this person can now a chance to show the card or scratch the card, and next he can enter into the ATM machine room. Okay, and then semaphores. Semaphores are the best solution for the critical section problem. So semaphores are also called as synchronization tools. Okay, so what is a semaphore and how can we represent it? Semaphore is a synchronization tool. Usually we call it as S. We call it with letter S. S indicates semaphore. Here the semaphore is a variable. It is initialized to either 0 or 1. If it is a binary semaphore, binary means two values. The semaphore can have two values. What are those? A semaphore can have 0 or semaphore can have a value 1, 0 or 1. Okay, that is called as binary semaphore. Okay, what is counting semaphore? Counting semaphore means other than 0 and 1, other values are also allowed, 2, 3. That means it is not only 0 and 1, we can keep some other value. That is called as counting semaphore. Okay, initially we need to talk about we need to talk much about the binary semaphores. We no need to worry about the counting semaphores. So up to now we need to concentrate on binary semaphores. So how many values a semaphore can have? A semaphore can have a 0 value, or it may can have value 1, 0 and 1. So that is the reason why it is called as binary semaphore. And next, on the semaphore we can perform two operations, and those operations are atomic. So what are the operations? Wait operation and then signal operation. So two operations. Remember, what are those? One is a wait operation. So here observe, follow the cursor. One is a wait operation and the second one is the signal operation. Okay. Whenever you want to enter into the critical section, you need to be able to perform the wait operation. Whenever you come out of the critical section, you need to perform signal operation. Are you got my point? In a similar fashion, whenever you want to enter into the critical section, you need to acquire the lock and then enter into the critical section. While coming out of the critical section, the process need to release the lock. Similarly, here also, whenever the process want to enter into the critical section, the process need to perform wait operation on the semaphore. S means semaphore, wait of S. Semaphore value initially set to 1. Remember one more time, the semaphore value is initially set to 1. Whenever the process wish to enter into the critical section, it need to perform the wait operation. Okay. So what is wait operation? Wait operation means decrementing the semaphore value by 1. Decrementing the semaphore value by 1. Okay. What is signal operation? Incrementing the semaphore value by 1. Incrementing the semaphore value by 1. So let me explain you with the help of paint. So what is a semaphore? Semaphore is a synchronization tool. How can we represent the semaphore? With S. And next, how many values a semaphore can have? 0 and 1. Binary semaphore. Why? Because it can hold only two values, either 0 or 1. That is the reason why it is called as binary semaphore. So these are the two values, and then one more point. So what are the operations you can perform on semaphore? What are the operations? You can perform two operations. One is wait and the second one is signal. Okay. So initially the semaphore value is 1. Okay, that means the value of S is 1. Whenever the process is wish to enter into the critical section, it need to perform the wait operation. What is wait operation? Wait means S minus minus. What is signal operation? Plus plus. Wait means decrementing the semaphore value by 1. Decrement semaphore value by 1. So what is signal operation? Incrementing the semaphore value by 1. Okay. S minus minus means S equal to S minus 1. S plus plus means S equal to X plus 1. That means wait means decrementing the semaphore value by 1, and signal means incrementing the semaphore value by 1. What is the initial value of semaphore? 1. Whenever the process is wish to enter into the critical section, it need to perform the wait operation first. That means what is the order? So first the process has to perform the wait operation, and then if it is able to perform, if it is able to perform the wait operation, then the process is allowed to enter into the critical section. Okay, whenever it is coming out of the critical section, it need to perform signal operation. Are you got my point? So whenever the process is wish to enter into the critical section, it has to perform the wait operation. If the process is failed to perform the wait operation, then the process is not allowed to enter into the critical section. Okay. Initially the S value is 1. So here for example there are two processes P1 and P2. So now P1 is willing to enter into the critical section. What it has to do? The P1 has to perform the wait operation on S. So that means in order to perform the wait operation, you need to check. What you need to check? S is less than or equal to, if S is less than 0, if it is less than 0, so automatically do nothing. The process cannot perform anything. Okay. If it is not less than 0, then what it can do? It can able to decrement the semaphore value by 1. So after coming out of the critical section, the process has to perform signal operation on S. That means S plus plus. What it is exactly? Whenever the P1 is beginning to enter into the critical section, initially what is the value of S? S value is 1. So 1 is less than 0. So condition fail. So automatically not do nothing. So what it can do? S minus minus. What is the S value initially? 1. So 1 minus minus means 0. That means what is the S value now? S value is 0. Whenever P2 is also wish to enter into the critical section, what it has to do? It is also need to perform the wait operation. Okay. Equal to 0. So whenever it is S less than or equal to 0, what is the value of S? 0. 0 less than or equal to 0. Why? Because already P1 perform wait operation on semaphore S. So the one value becomes 0. So again P2 is also wish to enter into the critical section. So it is also need to perform the wait operation. So wait operation you need to perform on semaphore. What is the value of semaphore? 0. So if it is 0, we cannot decrement it by 1, right? 0 minus minus we cannot perform. 1 minus minus we can perform. Why? Because 1 minus minus means we need to decrement the value by 1. So it will become 0. 0, 0, 0 minus minus means we cannot perform. We cannot decrement the 0 value. Right? So what can the process 2 can do? Process has to block. Why? Because it cannot perform wait operation. Okay, that means whatever the process can able to perform the wait operation, that process is allowed to enter into the critical section. So in our example, first P1 perform the wait operation, so the value become 0. After, so the process 1 is allowed to enter into the critical section. So after that, process 1 need to perform the signal operation. What is signal operation? S plus plus. What is the value of S? 0. So 0 plus plus means again the semaphore value become 1. At that time, the P2 process has to perform wait operation. Why? Because P2 is blocked now. So whenever the semaphore value become 1, automatically there will be a signal went to the P2 process. Okay, so then at that time P2 will perform the wait operation. Now the value of semaphore is again 1. So 1 is, sorry, no, sorry. So 1 is greater than 0. Now the 1 is greater than 0, right? So whenever it is greater than 0, so automatically what we can do? We can decrement the operation, right? If it is less than 0, do nothing. But here the what is the value of 1? What is the value of semaphore? It is 1. 1 less than 0? No, 1 is greater than 0. So the condition is fail. Whenever the condition is fail, automatically we need to move to the this statement. So S minus minus, 1 minus minus. So P2 is able to perform the wait operation. So P2 is allowed to enter into the critical section. At that time, another process P3 might come. So what P3 has to do to enter into the critical section? Again, P3 need to perform the wait operation. Okay, but it cannot perform the wait operation. Why? Because the S value is 0. So we cannot decrement the S value to S value by 1. So automatically P3 has to wait until P2 performs the signal operation. Okay, after using the critical section, again P2 will perform the signal operation. Again, it will increment the value to 1. Likewise, only one process is allowed to enter into the critical section. Only one process. Are you got my point? Are you got my point? Very simple and very important too. With respect to gate and with respect to interview also. Right? So what the thing? So semaphore initially set to 1. How many operations we can perform on semaphore? 2 operations. One is wait and the second one is the signal. What is wait? Wait means decrementing the semaphore value by 1. What is signal? Incrementing the semaphore value by 1. Okay, these are the operations. Whenever the process P1 is wished to enter into critical section, not only process P1, any process is wished to enter into the critical section, it has to perform wait operation. Okay, if it able to perform, then it is allowed to enter into the critical section. So after using critical section, what the process has to do? Process has to perform signal operation. So that is a thing. Here it is a binary semaphore. Binary semaphore means either 1 or 0. Okay. Are you got my point? For example, there are two processes P1 and P2. So P1 is willing to enter into the critical section, so it performs the wait operation. So what is wait operation? It performs wait operation on semaphore S. In order to perform the wait operation, we need to check the condition. What is the value of semaphore? While S less than or equal to 0, less than 0. So automatically what we can do? We cannot do anything if the semaphore value is 0. Why? Because initially it is set to 1. What is the value of semaphore now? 1. So 1 is less than or equal to 0. Condition fail. So we should not enter into the while loop. So S minus minus. So we can perform the minus operation. Then 1 become 0 now. So after that, the process is enter into the critical section. Right? After using the critical section, what the process has to do? Process has to perform the signal operation on S. What is signal operation? Incrementing the semaphore value by 1. So whenever P1 is in critical section, what is the value of S? 0. Why? Because before entering into the critical section, we decrement the semaphore value 1 to 0. Why? Because 1 minus minus becomes 0, right? So when the process is in critical section, so other process P2 want to enter into the critical section. At that time, what P2 has to do? P2 need to perform the wait operation. So wait of S means here what is the value of S? 0. So we cannot perform wait operation. P2 cannot perform the wait operation. Why? Because the semaphore value is already 0. We cannot decrement the 0 value, right? So what the P2 has to do? P2 need to block, right? Up to what time? So whenever P1 completes its critical section execution, it will move to the signal operation. Whenever it performs the signal operation, the value of S0 plus plus means 1. Again, the semaphore value become 1. So there will be a signal to the P2 process. So now the semaphore value is 1. So it can able to perform the wait operation. Why? Because 1 minus minus means 0. Again, the P2 will be entered into the critical section. At that time, P3 process might come into the picture. P3 is now want to perform the wait operation, but P3 cannot perform the wait operation. Why? Because P2 already decrement the semaphore value to 0. So if it is 0, P3 cannot perform the wait operation. So the process which are not able to perform the wait operation are unable to enter into the critical section. Okay. Whenever the process enter into the critical section, while come out of the critical section, the process need to perform the signal operation. Again, the value become 1. Then the blocked process will be able to perform the wait operation. Likewise, only one process at a time can enter into the critical section. So those are the operations. Wait operation, perform the wait operation, enter into the critical section, and then perform the signal operation. Whenever a process want to enter into the critical section, the process has to follow the same thing. Perform the wait operation and then enter into the critical section. While coming out, it has to perform the signal operation and then reminder section. Okay. So this is the order. First able to perform the wait operation and then critical section and then signal. Same thing. What I told you, the same thing. Okay. So here we are having a variable called as mutex variable. So what is mutex? Same thing. Here we are in the earlier example we said semaphore as a semaphore with a symbol S. We represent the semaphore with the symbol S. Sorry. So here there is only one more variable called as mutex. Mutex means this is a semaphore variable. So what is the value of mutex? Initially the mutex value is 1 like semaphore value. So what we need to do? We need to perform the wait operation on mutex. Wait of mutex. and then you need to enter into the critical section. While coming out of the loop, critical section, what you need to do? You need to perform the signaler operation on mutex and then reminder section. Okay, this is the code part. Okay, whenever the process enter into the critical section, automatically need to perform the wait operation. What is wait operation? Decrementing the value by 1. What is the mutex value? 1. So 1 minus minus becomes 0. So the process is able to perform the wait operation on mutex. Why? Because the value of mutex is 1. So it will enter into the critical section. So while it is in the critical section, some other process P2 came into picture. It is also try to perform the wait operation on mutex, but it failed to perform the wait operation. Why? Because the mutex value is 0 now. So the process has to wait or block. Okay. So P1 is now in the critical section. After using the critical section, P1 will perform the signaler operation on mutex. What is the value of mutex? 0. Signal of mutex means 0 plus plus. What is the value? 1. So P1 will move to the reminder section. So whenever the mutex value become 1, again P2 is able to perform the wait operation. Now, why? Because 1 minus minus you can perform. So like that, P2 can perform the wait operation and enter into the critical section. So that is the thing. Likewise, only one process always there in the critical section at a time. Why? Because two process cannot perform the wait operation, right? Only one process can perform the wait operation. So why? Because the value is 1. We can decrement it by 1, automatically it will become 0. Other process cannot decrement the value, 0 value, right? So only one process can enter into the critical section. Whoever the process able to perform the wait operation, that is allowed to enter into the critical section. After using the critical section, it has to perform the signal operation. In the earlier case, we represented semaphore with S. Now here there is a variable called as mutex, synchronization variable mutex. It is set to 1. So instead of wait of S, wait of mutex. Instead of signal of S, signal of mutex. Wait of mutex means mutex minus minus. Signal of mutex means mutex plus plus. Wait means decrementing the value by 1. Signal means incrementing the value by 1. Right. One more thing I want to tell you. Whenever P1 is performing wait operation and it is enter into the critical section, after that it has to perform the signal operation, right? These are the order of operations. So whenever P1 performs wait on mutex, what is the value of mutex now? The mutex value is 0. Why? Because initially mutex value is 1. Performing wait operation means decrementing it the value 1 and it will become 0. So whenever it is 0, maybe P2, P3, P4, these processes are also willing to enter into the critical section. So every process is try to perform the wait operation in order to enter into the critical section. But the semaphore value is 0 now. Why? Because P1 is decrementing it decremented the mutex value to 0 already. So P1 is in the critical section now. So all these process, where these process will be, these processes are waiting in a queue, blocked. That means these are added to list. P2 try to enter into the critical section. So it want to perform the wait operation but unable to perform the wait operation. So P2 is added to list. And then P3 is also willing to perform wait operation, unable to perform the wait operation. P3 is also added to list. And P4 is trying to enter into the critical section, but it unable to perform the wait operation. Why? Because the value of semaphore variable is 0. So P4 is also added to the list. Like that, all the waiting process are added to the list. So whenever the P1 completes the critical section execution and it will perform the signal operation, again the 0 will become 1. Why? Because 0 plus plus means 1. Okay. So at that time, what you need to do? We need to remove one process, remove one process from the list. Why? Because now the value of semaphore is 1. So the process can make it 0. The process can perform the decrement operation. That means wait operation. So one process is removed from the list. Are you got my point? Whenever the process are waiting, unable to perform the wait operation, then those are added to the list. Whenever the signal operation done by the process which is coming out of a critical section, so automatically one process will be removed from the list so that it can able to perform the wait operation now, and then it can enter in the critical section. Likewise, all the process which are unable to perform the wait operation will be added to the list. This is the one. Wait of semaphore. So here is a pointer. So what is the value of semaphore initially? Value is 1. Value 1 minus minus means 0. So if the semaphore value is less than 0, that means we cannot perform the wait operation. So add the process to the list, and we need to block the process. What is a signal? Whenever the signal means increment in the semaphore value. Whenever it is become equal to 0, and whenever it will become more than 0 or equal to 0, automatically we can remove the process from a list. Are you got my point? We need to wake up a process. Here we are unable to perform the wait operation, decrement operation. So we need to add the process to the list. So whenever there is a signal, the process can be perform the wait operation. Why? Because the semaphore value become 0 more than 0. So automatically the process will be removed from the list. Likewise, all the process which are failed to perform the wait operation will be added to the list. Once the signal operation is done, one process from a list will be removed. Deadlock and starvation, this thing we will discuss in the tomorrow's class. Why? Because it's already 10:22. So you might have another class. Do you have any doubts? Let me know via WhatsApp. Or you can inform any of your faculty so they can convey the information to me. Thank you.